Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Eda Gjergo with us today. I said it right.
Frank, I'm so happy to be here.
Well, Eda, thank you so much for talking about your very lovely article. And where are you located at? What's your geolocation?
I'm in Nanjing, China.
China, we're halfway around the world. Awesome. And our bandwidth is pretty good too. We only have like a 2-second delay, so it's pretty awesome.
It's great. It's great.
Let's see. Is spring in the area out there, or we still have snow on the ground, or what are we doing?
We haven't had any snow, and yeah, there's the sun out. It's a lovely weather. It's finally starting not to be cold anymore. So yeah, things are great.
Very cool. Things are good. I like that. It is March 7th of 2023 as we record this. I'm in Phoenix.
March 8th for me.
March 8th for you. That's right. We got to pass the date lines. Very cool. Yeah, and spring is in the air here. We are definitely undergoing a transition. So we're getting lots of wind as we get the battle between the Gulf Coast air and the air from the north, and they're doing their battle, and we are in spring. So it's very cool. And Eda, what do you like to do for research?
What do I like to do for research? Yes. So this past few years, I've been interested in studying the evolution of chemical elements. And that is a topic that you're very well familiar with, because I believe that you have been the first person to write a publicly available chemical evolution code. And it has been a point of reference. So here I'm a little humbled to describe this new generation code to the first person who made it public. So,
well,
yeah.
I appreciate your compliment. Thank you very much. But I'd much rather hear about your new one than some kludgy thing.
I'm very happy to discuss about that. Okay. Yeah.
And that is going to bring us to this very awesome APJ supplement article. It's open access, people, so you can go get a copy, grab one. GalCEM 1. Yeah. An open source, detailed isotopic chemical evolution code. And Eda, take us away.
Thank you. So we decided to name it GalCEM. And actually, while I was a PhD student, I worked on cosmological simulations, but I had a very close rapport with Francesca Matteucci. And basically, this code is a little bit in honor of her legacy. And actually, this year, 2023, is going to be her 40th year of academic productivity.
Cool.
So,
yay, Francesca.
Yeah. So, all of these co-authors have been essential in the development of this code. And originally, the goal was to develop a very detailed rate equations for enrichment sources for our process elements. But while we were testing out different yields, we realized that the private codes were not suitable, were not flexible enough to seamlessly switch among different yields. Okay. So basically what we decided was to develop a code that would pre-process yields and basically would adapt the number of isotopes tracked according to the yield tabulation chosen. Cool. So yeah, basically this is the idea. So this is a code that was developed with nucleosynthesis people in mind. So actually there's, I will be describing an extra pre-processing tool that anybody can use. Cool. And I will show why that speeds up our computations. Okay. Yeah.
Very nice. Yeah. Very nice.
So, and actually, I just wanted to spend a few words in general about what is galactic chemical evolution. Okay. And for the people who will read the abstract, you will notice that this is just the first in a series of papers that we have planned, and hopefully GalCEM can have countless applications in the years to come, and we already have several students that are working on this.
Very nice. Very cool.
So me coming from cosmological simulations, it was a little bit difficult to get into the mindset of galactic chemical evolution, because cosmological simulations, they produce stars, star particles with a certain stochasticity, and then the star particles are treated like single stellar populations, and they project the chemical enrichment into the future.
Yes.
While galactic chemical evolution has a different approach. So it has this backward approach. So at every time step, you reconstruct how stars were born in the past and where do they die now. Okay, so I just wanted to make this preface that conceptually is different.
Yes.
And it is an analytical model, but it is still very powerful because it allows in a clean way to test hypotheses that eventually are also used by people in cosmological simulations, right? So through analytical models, it's possible to isolate and truly understand what these models that we end up eventually putting into the cosmological simulations, right? So the point is, how does it all make sense, and how does this model behave in isolation? So this is the goal of galactic chemical evolution.
Good.
And it has had a very long history. Here I mention Salpeter, 1955, the first paper in which the initial mass function was introduced as a concept.
Yep.
And eventually we will later on arrive to the B squared FH paper, the Burbage-Fowler Hoyle paper.
Yes.
But basically, I just wanted to say that it has been a field 70 years into the development. And with this paper specifically, we wanted to reach a benchmark. So it is a one-zone model.
Yes.
But the foundations were laid out in the 50s and 60s. So over there, one of the symbols that you'll soon be hovering in the next paragraph is the birth rate function, which is one of the key concepts. So the birth rate function is represented as the product of the star formation rate with the IMF. So in this first computation, we make the ansatz that the time component and the stellar mass component are separable. Okay, so the star formation rate captures the evolution through time, and the IMF captures the distribution of stars. Okay, so the product of this will give us how the function of the birth of stars varies with time.
Yes.
And I think we can scroll to the first figure, which will be representative of the whole rationale of chemical evolution.
Very nice. Right? Very cool. Okay.
So we have a time on the x-axis, so both with the orange line and with the red lines. With the orange line, I show how the star formation rate changes with time. So the star formation rate tells us for the whole galaxy, because for us a galaxy is homogeneous, so it's a single point, right? So for the whole galaxy, how much gas mass is converted into stellar mass? Okay, so it's a rate. But the actual distribution of this total mass into individual stars is captured by the initial mass function. Okay, so that birth rate, the initial mass function is on the y-axis, and on the x-axis you have the star formation rate. So you can imagine this three-dimensional birth rate surface.
Yes. Okay. Cool.
Chemical evolution doesn't care about the birth rate function. It cares about the death rate function. Okay, so by means of lifetimes, you project this birth rate function into a death rate function. And then slicing through time this death rate function, this is how you get which stars died at which time step. Okay. And this is shown by the diagram, both at the Tn and the Tn+1 time steps. So for every time step, you repeat this reconstruction. Okay, so over here, the bluer the star, the more massive it is, and therefore the shorter the lifetime, they will die sooner. So basically, the more massive stars will have been born not much earlier than the time step considered, while at that same time step, Also, stars that were born much earlier will die also at that time step. So basically, this is the idea. And just notice this other thing, that metallicity will change with time. So along with star formation rate, you would have a metallicity function, which is time dependent. So each one of these stars that were born in different single stellar populations, they would have a different metallicity.
Yes.
Okay.
You gotta track that.
And over here, in light blue, I show the enrichment by core collapse supernova or supernova type 2. And then in magenta, the enrichment by low to intermediate mass stars, AGBs, basically. Okay, so this is the division. And these are two of the main processes involved in galactic and chemical evolution. So you always need these two to capture the low mass end and the high mass end. And you also need type 1a supernova. And type 1a supernova are essential because they produce between half to 2/3 of all of the iron that exist in the galaxy, or probably at a cosmic rate. So it is essential to have a good description also of how type 1a supernova evolve with time and how they enrich the medium. Okay, so this is the whole rationale.
I'm with you.
Yeah. So yeah, I mentioned already the Burbidge paper, the B2FH paper.
Sure.
And later on, I give a little bit of an overview of some of the successes that there have been many of galactic chemical evolution, and also the advancements in the computations, right? Because here, even though I'm presenting this one zone model to reach this benchmark, there are already several people who have developed multi-zone model, radially dependent model, inhomogeneous models, Bayesian approaches. And originally, the galactic chemical evolution was a closed box model, but then from Kyoshi onwards, I believe Kyoshi might have been one of the first people. Basically, he introduced gas inflow and outflow, and also this is extremely important, and it is proven over and over from observation that outflows do carry lots of chemical enrichment into the intergalactic medium. All right. So basically, this all through this analytic modeling, it has been able to capture very, very successfely several of several observational properties of interest. All right.
Yes.
So over here, once again, this isn't the only publicly available code. So we decided to develop it in order to follow the formalism introduced by Francesca Matteucci. But there are many other publicly available codes. There's NuPyC, the Omega package. So the Omega package within NuPyC is one of the most modern and most popularly used codes. There's another code called GalIMF, which introduces a variable IMF within the IGIMF formalism within a chemical evolution code. There's VICE, which is very well documented. But basically, all of these didn't suit our needs to switch seamlessly to the size of the yields, because in the next paper that is to come, hopefully paper 2 or maybe paper 3, we will be given an overview of the entire periodic table, and we will explore in detail individual R process elements. So we really needed to have as complete and as thorough of an overview of the production of all of the chemical elements.
Cool.
All right.
Okay, I'm with you.
Yes, galactic chemical evolution now has finally reached its golden era with all of these very detailed
Ah,
surveys.
yes. Right.
We have Lamust, we have Gaia. It's really unprecedented here. I'm showing the full list of surveys that have investigated chemical tagging, and we have really reached an era where there's very vast libraries of stars, of individual stars that maybe contain 20 elements or more for each individual star. So it's really it's really a fantastic era to be working on galactic chemical evolution.
Nice.
But all of this is to come in the future. This paper is only about presenting what the original formalism of this one zone model is. So maybe let's get ahead and describe that formalism.
Let's do that.
So, all right. So with figure one, with equation one, we have the rate of for each isotope I. How does the mass of the ith isotope change in the ISM?
Okay.
Right. So basically, how what ends up contributing to the gas mass abundance of isotope I? Obviously, there's that astration component that you're highlighting. So we have an inflow at the beginning. This inflow component will not have the same composition as the galaxy, right? And we assume that the inflow component has a primordial abundance.
Big Bang. Yep.
Yeah. And we will show later on what inflow prescription we adopt. Then there's going to be the outflow at the very end of the equation.
Yes.
As we already mentioned. So we have to have gas coming in, and we have to have gas coming out.
Okay.
Then stars will form. Yep. So we have the star formation rate component. From the gas mass of isotope I, we subtract only the fraction of gas mass of that given isotope, because obviously the gas will not care what elements it will absorb into the star component.
Right.
Yeah, so this is what we're subtracting. But obviously, when stars die at that same time step, we will have a return rate for each process P. So basically, this is very simple. Inflow, astration, return rate from dead stars, and outflow. Okay.
Good. Easy enough.
Yeah, and all of these P processes, for this specific paper, we said are the low emitting mass stars, the AGBs, which are AGBs, it's the same thing, Corculopsis supernova, and type 1a supernova.
Yep.
Yeah.
There's 4. Okay. And I think it looks like we're going to summarize that a bit in table 1. Okay.
Oh, and we're already at table 1. Perfect. Yeah. And here there are several symbols, and I do want to spend a few words on this table, just so that we can avoid confusion later on.
That's a good thing.
So there's several indices. So I tracks the isotope.
Okay.
K tracks the mass grid, which will make sense once we get to the rate equations.
Okay.
N tracks the evolution through time. Okay. And capital P tracks the different astrophysical process. Okay. Then we get to the time variables. So TG is the final age of the galaxy. Right. T is the time variable, the quantity that we track. Then T prime and tau are respectively the birth time and the lifetime. Okay. So the lifetime is defined for a star of mass M and metallicity Z. Stellar evolution people tell us what the lifetime of that given star will be. So relative to each time T, the the birth time will be given by t minus the lifetime.
Yes.
In this equation, I've shown instead t minus birth time to represent a lifetime, because actually this is the quantity that is used in the rate equations. And so I wanted to highlight this definition. But
Okay.
the rationale is that lifetime comes before, and then birth time comes as a subtraction of t minus lifetime.
Okay. All right. Yes.
Then come the mass quantities.
Mhm.
So m star refers to the mass of a single star. Okay. And this is used in the integrals. Then we have the lower limit and the upper limit for each process, for each astrophysical process. Then we have the inflow mass, which will vary as a function of time.
Yes.
The gas mass, this is the total gas mass, which also varies as a function of time. And then we have the gas mass of the isotope I, which is exactly what I just said, is going to be a fraction of the total gas mass for each isotope.
Yes.
And then m star tot refers to the total stellar mass as a function of time instead of the individual one. Yeah.
Okay.
And then we have these other miscellaneous quantities. So nu refers to the stuff emission efficiency, and then we have the stuff emission rate, the IMF, metallicity, and the yields.
Okay.
Okay. And the yields will depend on the isotope, on the stellar mass, and on the metallicity, as described by the tables of nuclear physicists. Yeah.
Okay. Very good.
Right. So we can move forward. Yeah, maybe we can go directly to this other diagram just to describe how GalCEM comes together.
Okay.
Okay. So we described the presence of yields. Okay. And obviously, I also include Big Bang nucleosynthesis because the inflow gas is primordial. So there's that component as well.
BBN.
And of the upcoming components for the R processes, we have the neutron star mergers, magnetohydrodynamic jets, and collapsars. Yes. So, and in lighter gray are other processes that we will include further in the future.
All right.
And one thing that was important for us was to separate the individual point-like sources of enrichment.
Yes.
Versus the whole morphology of the galaxy. Because the point of galactic chemical evolution is that you have to integrate these individual sources over the whole shape and the whole history, the whole evolutionary history of the galaxy. So within the morphology classes that reconstruct our galaxy, we have the stuff emission rate, the IMF, the inflow, and the stellar lifetime.
Got it.
And then once we will change the description of the structure of the galaxy, this is also where the multi-zone classes will go.
Okay.
And then with the input classes, this is where probably the user will have the most interaction. So unless through the modularity of this code, people will want to insert their own equations, they're very welcome to do that. This code is publicly available. It's already on GitHub.
Cool.
But in case you want to use the functionalities already existing in GalCEM, then through the input classes, you can change the parameters.
Okay.
So all of these classes come together in the setup class that has to be instantiated at the beginning for each run. And then once you invoke the one zone class, this is where you're able eventually to start running the simulation. And within the one zone class, you can track the total evolution of gas mass and stellar mass and stuff emission rate and so on.
Okay.
While the isotope evolution tracks the return rates for each isotope.
Okay. Yes.
And isotope evolution will invoke both total evolution and isotope evolution will invoke the integration classes.
Yes.
Obviously, once the run is done, the output can be manipulated by already available plots in post-processing, so that's standard. Yeah.
Nice. Very nice. Good setup. Good setup.
Thank you. So we can scroll further down.
Okay.
Yeah.
See.
Yeah. So over there, you see the import. So this is, yeah. This is one of the minimal working examples of how to run GalCEM. And then you will see in the other, on the second column, you have inputs.end time step.
Uh-huh.
So before starting your run, you can change your input parameters without having to put your hands into the code, but directly from your terminal.
Yes.
You can change these parameters. So basically, all of the parameters are completely customizable. They're classes, modular, and we really put an effort to make it as user-friendly as possible.
Very cool. So
this is all that the setup is about. And obviously, if you want to install it through pip, so that you don't want to worry about any coding at all, you just want to use it as it is, just install it through this, and you can obtain whatever abundances you want.
Nice.
Yeah. Okay. All right. So yeah, we get to the inflow rate and to the outflows. Okay. And in equation 3, this is the representation of our inflow, and it's just an exponential decay. So this exponential decay will depend on the inflow timescale, tau inf. And obviously, this tau inf will be shorter for elliptical galaxies and longer for spiral galaxies. Okay. And this is in very, very good agreement with abundances of all of the main elements up until zinc for, over here I'm citing Pipino and Matteucci for elliptical galaxies. And Molero in 2021, she published these 2 papers on the abundances of our process elements for different morphologies. And so within this formalism, the Milky Way, the thin disk of the Milky Way is well reproduced by an inflow time scale of 7 gigayears, while elliptical galaxies would have a time scale of 0.2 gigayears.
Much smaller. Okay.
Yeah.
Cool.
All right. So the total mass will simply, the actual total mass, so from time 0 to the lifetime, to the final age of the galaxy, will simply be given by inflowing mass minus outflowing mass, and this is the total mass.
Okay, sure.
Now, for this specific paper, we assumed that the outflow is 0, and in a later section, we will explain why that is.
Okay.
But in case the inflow, in case the outflow is 0, equation 5 shows very simply how the total mass and the inflow mass coincide with this hypothesis.
Okay.
So for us, our galaxy has an age of 13.7 gigayears with this inflow time scale of 7 gigayears, and a total mass of 5 times 10 to the 10. So one thing that I would like to highlight is that we do not have dark matter, because we do not treat any dynamics, so we do not have any gravitational component. So for us, we only care about the baryonic component. Okay. So yeah, this is the baryonic mass.
Yes.
Okay. And as I have mentioned earlier, outflows have been shown to exist and to be enriching the intergalactic medium. So in this paper by Cameron 2021, the outflow mass is actually 1.6 times supersolar in terms of metallicity abundance. So yeah, this outflowing masses can be very much
Metal rich.
rich, yeah, metal enriched. And ever since 1978, there was the hypothesis that indeed the chemical enrichment that you observe in the intracluster medium is derived by the outflow of galaxies.
Yeah, good.
And there are some authors, Andrews, Weinberg, that show within their models that outflows do have a significant impact on the chemical evolution. But there are also other people, especially the one working with our formalism, that show a couple of things. On one hand, Spitoni, 2008, shows that he made some studies on galactic fountains. And so even though you might have this enrichment will fall back roughly around the same galactocentric regions.
Okay. All right.
Yeah. And furthermore, the time scales of these outflows should be of 0.1 gigayear. Maybe if we scroll up, I can confirm that number.
Yeah, that's about right, about a tenth.
Yeah. And so basically, so this was done in 2009, always by Spitoni. And basically, with these time scales, the outflow within this formalism appears to be negligible.
Okay.
And in fact, there are several the modelers that have confirmed that they were able to correctly reproduce observations. Yeah.
Same as outflow. Okay.
Yeah.
All right.
Now, in GalCEM, the outflow function exists, and we adopted the Bradamante 1998, so that the outflow is equal to this omega parameter multiplied by the stuff emission rate. So the assumption is that the stuff emission rate drives the outflow with a certain coefficient that has to be between 0 and 1. Okay. Depending on the specific needs. But I'm overriding in the code this with 0. But
sure.
Obviously, this can be easily edited. And actually, we already have several morphological options. So if one chooses either some satellite galaxies, there's Fornax. You have a general spiral Milky Way-like galaxy, an elliptical galaxy, and a regular galaxy. So basically, by specifying the morphology already, there are several parameters that have been calibrated for GalCEM and this formalism in general.
Very cool.
So users can already do that.
Very nice.
Then we get to the initial mass function.
Okay.
Which is one of the first components of the birth rate function. So the initial mass function basically represents as a function the number of stars that exist as a function of stellar mass. And in chemical evolution, and this is different from other studies, you have to normalize the IMF, the mass-weighted IMF, to 1. Because the stuff emission rate is already capturing what's the total stellar mass in terms of solar masses that is converted into stars as a function of time. So the IMF should be normalized to 1 so that you do not introduce any other rescaling. Okay.
All the units are carried by the star formation rate.
Exactly, precisely. And in GalCEM, we do have the salpeter option, and we also have the Krupa option, which is the universal IMF. It's the canonical representation of how the average IMF for the Milky Way looks like. So this is our current assumption. And obviously, all of these parameters can be edited if necessary. And actually, I'm just going to give a little bit of an advertisement of what we're doing in the future, because I am, in fact, I'm developing another code for the IgIMF, so for a variable IMF. And so, actually, I have a student right now that is working on implementing that code into GalCEM. Nice. So soon, one of the one of the first applications of GalCEM will be that of a variable IMF,
Okay.
which here in Nanjing, if I can do a little bit of an advertisement, there was last month a Nature paper in which they show irrefutable evidence that the IMF has varied as a function of metallicity in the local solar neighborhood.
Okay.
So this is very exciting. So this is why our group is very much pushing forward to applying a variable IMF also on chemical evolution codes. Yeah.
Okay. Nice.
Yeah. And then we get to the star formation rate, which is the second component of the birth rate function.
Indeed.
And this is just the typical Kennicott-Schmidt definition. Yeah, so we have the star formation efficiency, nu of units of giga-year to the -1.
Yes.
And here you see that it's, in this specific representation, there's no mass unit, because you see that the gas mass is normalized by the total mass.
Right.
Okay, so that you can elevate it to whichever power you want. And for the Milky Way, the best fit is 1.4, even though in my code I use 1.
Okay.
Because it seems that the whole community is starting to gravitate towards using k equals to 1. Okay. And so just to reach a benchmark, this is what I did.
All good.
This paper is not meant to reproduce all of the chemical abundances right now. That's for the future. This is just
good. Yep.
Yeah.
Check out.
So afterwards, I have just a little bit of algebra. I thought it couldn't hurt just to show specifically how I converted from Portinari to what is actually present in the code, which is in equation 11. And the assumption over here, which might change in the future, or will have to change in the future once we have a multi-zone model. Yeah. Because over here, I could do the simplification, assuming that the surface area doesn't change with time, because we only have 1 point. Okay.
Right. Okay.
So,
okay.
Yeah.
I'm with you.
So,
I'm with you. Okay.
Yeah. So over here, this version of the star formation rate equation 11, normalizing by the final mass, is necessary for the rate equations. While when I have to do the integrals for the total gas mass and the stellar mass, I remove the final normalization so that the units of the star formation rate is solar masses per giga-year.
Correct. Okay. I'm with you. Yeah.
Yep. Okay. So we've seen. Now we have our birth rate function. We need to get our death rate function, and we do that through the stellar lifetimes. And the stellar lifetimes are in figure 3. Which is a little above.
Figure 3. Here we go.
Yeah, we just passed it. Yeah.
Sorry.
So on the top panel, there's the actual lifetime as a function of stellar mass and the metallicity of each stars. And you see that if you plot it with respect to the mass, the variation in metallicity seems very, very small in the log-log scale.
Right.
On the vertical axis, I just have some sample reference masses of 3, 6, and 9 solar masses.
Oh, got it. Okay, I'm with you. Okay.
While on the bottom panel, this is a linear ratio, which on the specific lifetime normalized by the lifetime at the lowest metallicity.
Okay.
Which is the black line in the above plot.
Okay. Okay.
And so you see that generally the closer, the lower the metallicity, the closer this ratio is to 1.
Yes. Okay.
And so you see that, especially for the high mass stars, you see that the metallicity, the supersolar metallicity, which is the solid line in the bottom panel, is the lowest one. And then as you increase, you get closer and closer to the horizontal ratio of 1.
Right. Okay.
Well, for the low to intermediate mass stars, I'm sorry?
So the differences are bigger than it looks up in this log plot.
Yeah, it is. It is. And I just wanted also to highlight the fact that in the log plot is not evident, is that strangely enough, this trend that you see for the high masses is not reproduced for the low masses, because you see that for the low masses, the solar metallicity actually has the highest ratio. So basically, the solar lifetimes are much higher compared to the lifetimes at the lowest metallicity compared to supersolar metallicities. And basically, this is caused by a combination of the fact that a supersolar metallicity, you have a higher molecular weight because you have less hydrogen, and you also have a higher luminosity. And these two facts combined cause a decrease of the lifetime for low mass stars. Yeah. So this is a quite interesting fact that for supersolar metallicity stars are going to be living a shorter amount of time compared to solar metallicity stars.
Very good. Cool.
Yeah. So, and this color coding is going to carry over in one of the next plots.
Okay, so let's get that color coding in our
that's logarithmic.
Okay, from blue to brown. Okay, I'm good. I'm good.
Yeah, so basically this means that the high mass stars will live 4 million years, and the low mass stars will live up to 10 billion years.
Yeah.
It's logarithmic, the scale. Yeah.
Okay, I'm with you. Very good.
Right. So we can scroll further down.
Okay.
And we should be soon getting to some of the interpolations, which are the special things about GalCEM. Oh, and here is just a little plot in which I show all of the isotopes that are included in this run. So we said 451 actually should be 75, but it's okay. It's a little typo, no problem. So on the y-axis, we have the proton numbers and the atomic mass on the x-axis. So usually nuclear physicists will show the number of neutron, but here, yeah, I'm just showing the atomic mass directly.
That's fine.
And the 3D plot is exactly the same information, and I just wanted to highlight to plot it in this way to show that the more we increase in atomic mass, the more the mass becomes equally distributed across different isotopes. So you see that for the low mass stars, you have a handful of isotopes that dominate all of the abundance, while as you increase in atomic mass, more isotopes are spread, are abundant to equal extent.
Yeah. Okay. Yeah. Good.
Yeah. So we get to the yields next, and the yields that we adopt in GalCEM. For the low to intermediate mass stars, we use Cristallo 2011-2015, while for the massive stars, we use Limongen Keffi 2018, which contain also contain also the yields for rotating massive stars.
Okay.
Which are going to be relevant in the future, even though for this benchmark we just take the yields at a 0 metallicity, because that's going to be another paper how to include the initial rotational velocity of the stars.
Okay. Good. Good. I'm
right.
Around.
So okay, we can scroll further down.
Okay, so yields and 1As. Here's some inputs.
Yeah. So in the inputs, I just use this this nomenclature, and basically this nomenclature is consistent with the nomenclature that you will find in the yield interpolation tool.
Oh, okay.
But this is detailed. So if people are interested in running different yields, they, with very, very little data manipulation, they can make it suitable for the format then accepted by GalCEM.
Okay. Very cool. Good. Yes.
All right.
We got almost all our ingredients.
Yeah. So we finally get to the rates, which is one of the most intricate part of chemical evolution, because
Yes.
it contains convolution integrals. So convolution integrals might be scary to some, and I have to say convolution integrals of chemical evolution are particularly scary because they're not plain convolutions. So there's functions of functions involved.
Yes.
But actually the idea is very simple, because convolutions are the natural way of reconstructing and stacking all of the past generations onto the time step that you're interested in.
Yes.
Okay. So you can treat the IMF as your impulse and your step formation rate as the function that gets smeared across the different stellar masses. And to the complication of chemical evolution is that you also have the metallicity variable. Okay, so given that the lifetime has a metallicity dependence as well, eventually there has to be a recursion to make sure that you're evaluating these integrals at the correct places. But I have a figure to show that in a little bit more detail. So basically, the idea is this: you have a rate, and you integrate it across the stellar mass. We don't actually do this. So this is the theoretical approach.
Yeah, sure.
Because you see that over here, the step formation rate is expressed as a function of time, and the IMF as a function of stellar mass.
Yes.
So how do you integrate the two? You have to make sure that you bring it to consistent variables. Yes. All right. And in between is sandwiched the yields, because also the yields, especially for core collapse supernova and for AGB stars, will vary according to both metallicity and stellar mass. Okay, and this is what actually we're interested in: how much mass fraction is returned by each one of these processes. All right.
Cool. Good.
We can move forward.
All right.
So this is the yeah. Oh yeah. And this is the general representation for low to intermediate mass stars and core collapse supernova. Type 1a supernova is something different, because type 1a supernova come from remnants. So is either the coalescence of remnants, or the application that I have in this paper actually is a single degenerate scenario. So basically you have a white dwarf that accretes from a companion, because you always have these binaries. So there's always binaries involved when you have delayed returns. And so
okay, cool.
Yeah, basically this is what you have. You have a white dwarf, and it accretes from a companion, and it exceeds the Chandrasekhar limit, and then you have the type 1a supernova.
Yes.
And here I follow equation 16 of Gregio 2005, and I really like this formalism, not only because Gregio is a long-time collaborator of Francesca, yes, but also because it's very initially computed. So it's a formalism that includes properties of both the primary companion and the secondary companion.
Yes.
And their envelope masses and their core masses. So it's a very detailed study about the specific evolution of white dwarf properties. So it's a very, very nichely done work. So the return rate of supernova is slightly different because there's no IMF involved.
Right.
There's the rate. The DTD of supernova type 1a represents, for a single stellar population, the distribution of the type 1a supernova events.
Right.
All right.
Times.
And also in this case, you have to do a normalization to 1, because once again, the step formation rate absorbs all of the mass information.
Yes.
And here, the progenitor of the type 1a supernova shouldn't exceed 8 solar masses.
Right.
Yeah. And here's another neat fact about type 1a supernova. The yield doesn't depend on lifetime or time in which the daily time distribution returns the rate. So it's basically fixed and can be extracted out of the return rate equation. So the return rate equation here is different because the integral is done with respect to the lifetime of the daily time distribution.
Right, not T.
Yeah. And I will, it's probably better if we skip the details about how the daily time distribution is computed, but if the reader wants to read it, it's very carefully computed
indeed
rate, because you have many other rates like Mautz and Manucci, in which you just get a power law. And eventually, this daily time distribution does also simplify to a near power law.
Okay.
But it's more sensitive to what happens in the earliest stages. And most of the chemical evolution blows up what happens early on.
Yes. Right.
So it's very important to have these careful computations.
Okay.
So here, in equation 18, once again, this is a callback to equation 1.
Correct.
But I write everything in a little bit more detail. So we have the info component, and we only take the fraction of the primordial gas for a given isotope I. Right. So basically, most of it is just hydrogen and helium. And so most isotope will have a 0 component of info.
Right. We're not accreting our process.
Yeah. And then over here, I explicitly write the Bradamante 1998 description of the outflow with the omega, which I set to 0, but 1 can also not. And then we have the summation of all of the various rates. Right. For that, all of the mass that gets returned from dead stars. So we've already explained this.
Yes.
So we can move forward to the next equations, and all of these x's are just mass fractions. I think I expressed that.
Yeah. Right. Okay.
So here it's one of the uglier, or I find it fascinating, equations in the paper. So it looks very confusing, but it's actually not, because here I simply did a change of variables. Yeah. From stellar mass, we've seen that the return rate was expressed in d of m star. And here, I instead do the computations with respect to birth time, because doing it with respect to birth time allows us to extract a computationally consistent grid, both for the star formation rate and the IMF and the yields. Yeah. So because the IMF will depend on the stellar mass, and the stellar mass will depend on lifetime and on metallicity at birth time. And this is explicitly shown in that phi m star of t minus t prime, which is tau. Okay. And z of t prime, which is the metallicity at the birth for the star. Correct. Which is what we care about. And that derivative that we have before of m star with respect to d tau minus, that minus sign comes from the derivative of the birth time, of the lifetime with respect to birth time. It's always minus 1.
Got a minus, yeah. Okay.
Yeah. And similarly for the yields, we have to make sure that we're computing the yields in the appropriate grid.
Sure.
And so you see that here, the convolution is still preserved, right? So you have all of these components that depend on the stellar masses.
Okay.
which are the IMFs, the derivative, and the yield. And then you have the stuff emission ratio, which depends on the birth time.
Okay.
Unfortunately, also the limits of integration depends on tau, okay, on the lifetime of the stars. So let's go to the next figure, which probably is going to help us understand this a little bit better, so we don't get confused and we don't get lost in the equations.
I don't want to get lost. Okay.
Okay, so this is hopefully a clear representation of what's going on. Okay, so on the vertical axis, we have the evolution of time, which is the magenta, the team. Okay. And all of the quantities that are tracked with respect to time are m tot, m gas, m star. So this m gas and m star are for the whole galaxy. And then you have the stuff emission rate and the metallicity. Okay. And then you have the evolution of the individual isotopes. So the squiggly line will represent the grid of the isotopes So on the x-axis instead, here we're looking at quark lapis supernova. So you will see that on top we have the stellar mass that goes from 13 solar masses to 120 solar masses for quark lapis supernova.
Here we are.
So these are the limits, for the Limongi yields.
Okay.
So this is how we do the computation. Basically, we have to compute grids, and all of the quantities of interest are computed in consistent places across this grid. Okay. So for this given lifetime, for this given stellar masses, we have a given lifetime, okay? And this given lifetime will trace us back to a given birth time.
Yes.
I put a tilde on that lifetime because we know that lifetime depends also on metallicity. So we can roughly estimate it, but not exactly.
Okay.
So we do it once. Then at these exact places, we reconstruct the IMF. Fortunately, the IMF depends only on the stellar mass, so that's not a problem.
Right.
And then you see that metallicity and stuff emission rate appear again. These are not the stuff emission rate and metallicity that you compute time step by time step. This is interpolated, right? Correct. So we have to reconstruct what was the metallicity at the time of birth of each one of these stars, and what was the stuff emission rate also at each one of these points. And so here is where I have a little recursion in the code that ensures that once all of this computation is done, you are within a margin of error at the correct metallicity.
Yes.
And at the correct lifetime and birth time.
Okay.
This is what you have. And you repeat exactly the same thing for low to intermediate mass stars.
Right. Okay.
And obviously, for low to intermediate mass stars, you will go from the yields go from 1 solar masses to 6 solar masses, but actually I have to extrapolate. So I do an extrapolation all the way to 10 solar masses to unite quark lapis supernova and low to intermediate mass stars. Okay. And I also extrapolate low to intermediate mass stars down to my lower bound for the mass range considered.
Right.
Yeah. Maybe so basically, this is how it goes. Low to intermediate mass stars will start to return contributions later on, right? Yes. So, and the squiggly lines are the rates.
Yep. Yeah. Cool. I'm with you. Good.
Okay. And here we see explicitly the N and the K. So K is the variable that identifies the grid for the masses, and N for time.
Yep. Very good. Okay. I like that one. Very nice. Okay.
So, over here, I invoke my mathematics degree because I was a math major as an undergraduate.
Oh, very good.
So yeah, so basically through this mapping process that I just explained, I basically get rid of the convolution. And so through a solution of Volterra equations and an application of the Simpson's rule,
Yep.
I'm able to just do my integral for the convolution.
Okay.
And now soon we will get to one of the reasons why my code is faster than the private equivalent.
Okay.
Yeah.
Okay.
So
out of hall.
So now we get to the interpolating surfaces, and I have to give credit to Alexei Sorokin, which is the second author, and actually he's a mathematics PhD at Illinois Institute of Technology, which was my alma mater in Chicago.
Thank you. Good.
And so over here in Figure 6 and Figure 7, we have the mass interpolant and the lifetime interpolant.
Right.
So basically, from Portinari 1998, we have our tables of lifetime and mass and metallicity. And over here, the top two panels, yeah. So if we can scroll, yeah, there we go. So in these top two panels, they represent two things. The bottom row is the original domain, so the raw data that are given by the table, so the one that look more whitish.
Okay. Okay.
And on the no, you were you can scroll a little bit. Yeah, these are the correct panels.
Yeah.
So you see that these are the colors that are consistent with figure 3.
Right.
And the transformed domain is in this first row, which is more colored. And basically, yeah, simply by doing some variable transformation, we were able to get to this place where we reconstruct a whole surface, you know, from this individual points. What GalCEM actually does is that it reconstructs this three-dimensional surfaces, and these are the three-dimensional surfaces onto which you do the computation.
Right.
Because as you've seen, most of our game consists in identifying your correct position in the grid. And if you want to do the interpolation at every time step for each isotope that you need, you don't need it for this lifetime, but you will see that we do the same thing also for the yields. It would be a mess. Instead, we pre-process both lifetime and the yields, so that we only have to read off information off of these surfaces. Okay.
Yes, all pre-computed.
So yeah, so this is what the mass interpolant looks like compared to the original domain of the raw data. And then if we scroll down, we have the derivative of the mass with respect to lifetime. Also this in transformed domain. So you can scroll even further.
Right, you're going to need that in this formalism. Okay.
Yeah, so those are the raw data, the one that the whitish parts. Yeah. Yeah.
Cool.
And right below in that parabolic surface, yeah, that's the derivative of the mass with respect to the lifetime in the transformed domain.
Yeah. Okay.
Yeah. And the whole black one is the derivative of the mass with respect to lifetime in the original domain. So in the original domain, you see that there are some places in which you risk to encounter discontinuities.
Yes.
And so it's dangerous when you have to do interpolations. That's why we had to invoke these transformations. Okay. Yeah, and exactly the same thing happens for the lifetime, and those are both. All of these quantities are necessary in the code in one place or another. Right. So yeah, that's the variation of the lifetime with mass and the derivative of lifetime with respect to mass.
Yes.
And with the odd rows, you have the transformed domain and the original domain, the planar spikier ones are the in the even rows are the original domain.
Okay. Okay. Cool.
So this is what happens for the lifetime, and
Cool.
basically the same thing is going to happen also for the yields. So we can scroll to the yield tables, to the yield figures.
Sure. Okay. There's one, figure 8.
Yeah. So this is for oxygen, and this is for Nanjing Kefi. So this is for massive stars, core collapses supernova. So the original domain is on the bottom row, and on the top row you have the transformed domain.
I'm with you. Yep.
And yeah, especially for the transformed domain, there is excellent agreement, which is actually, we report that in the appendix, so we can see how efficient this algorithm is in the appendix.
Okay.
And this is within the points, we calculate a bivariate spline, while we have a linear interpolation, a linear extrapolation outside.
Okay.
Yeah. And this saves us plenty of time because we're just reading off points.
Correct.
For each isotope. And actually, when we do the pre-processing, the tool that Alex developed will output each one of these surfaces in its own pickle file. So basically, for Limonge and Kefi, you have a few hundred files, and for the Cristallo, you have several hundred files for each one of the isotopes.
Okay. Got it.
But doing this work ahead of time saves lots of time later on to avoid interpolations. Yeah.
Correct. Oh, indeed. Oh, indeed. Okay, cool. Very good. There's our interpolators. And this is another one.
And that's precisely the same thing for the Cristallo 2015. Always for oxygen, it's the same idea. And you see that we had to work around that some of the points were not evaluated.
Right.
So in this plot, you can see clearly the difference between the bivariate spline interpolation within the data points and what you have outside, which is a linear interpolation.
Correct.
Yeah.
Okay. Right. So what else are you going to do with the whole? Okay. Very good.
Yeah. So we can move forward.
Yeah. Quantity. So, here we go.
All right. So yeah, these are the global quantities and the total quantities that we were discussing before. So over here, yes, we have masses on the y-axis and age on the x-axis. And here the age is linear and the mass is logarithmic. And the purple line right on top is the final mass of the galaxy.
Okay.
And we have the total mass in black. And as a sanity check, gas mass plus a stellar mass coincides with the total.
Yeah, better.
Yeah. And then we have gas in dark blue and M star in orange.
Okay.
And over here, you know that for the Milky Way, the ratio between stellar mass and gas mass should be around 10.
Okay.
But here is closer to 40.
Okay.
But if in the Staffordmation rate, you use, for the Kennicott law, you use a K of 1.4, you get 10.
Okay. Okay.
But here, just to follow the rest of the community, I use K1, and this gives you this higher stellar mass.
Right.
Okay.
Okay.
And I'm also showing other quantities. Probably the more interesting one is the metallicity magenta line, which is roughly 2 orders of magnitude lower than the total gas mass, which is what you expect. Yeah. And then we also have the total gas mass of each isotope, which, as another sanity check, has to coincide with the total gas mass.
Better the sum.
So
there we go.
Yeah, so those dots are the sum of the masses evaluated for each one of the isotopes.
Got it. Okay.
And then also as a reference, we have the total hydrogen mass and helium mass. In
these two, right?
Yeah, those two. Yes. Exactly.
Right. Okay.
And then we also have the rates. So over here, we have the infall, and even though it's an exponential decay, you see that the variation isn't excessive. So early on, you get to a level of 8 or 9 solar masses per year, and then you reach present time of 1 to 2 solar masses per year.
Yeah, right.
So it isn't very dramatic with the infalling time scale of 7 gigayears.
Right. Right.
And once again, given that the K is equal to 1, the star formation rate is parallel to the infall. And also parallel to the star formation rate is the rate of the core collapse supernova, because core collapse supernova, their progenitors are massive stars, which have a very short lifetime. And so as soon as they die, as soon as they're born, they die. That's why many people have the instantaneous recycling approximation. So they assume that core collapse supernova die instantaneously. But instead, that's something that is not often shown. For the low to intermediate mass stars, the contribution ends up actually being higher, but it comes with a little bit of a delay, because as we said, we get the return as a projection onto the time when the stars will die, and these stars will die later on.
Okay, good.
And then in light blue, we have the rate for the type 1a supernova, which come with a little bit of a delay compared to core collapse supernova. And obviously also with roughly, 1 order of magnitude lower.
Right.
Yeah.
Okay.
So these are all of the global quantities.
Cool.
They work as expected.
Good.
All is fine.
All is fine.
Is great.
All is fine. I like that. All is fine.
Yeah. So we can probably move forward to the next.
Now we're gonna hit age metallicity relation.
Yeah.
Okay.
Perfect. All right. So one thing that people who do not work on chemical evolution, they might not realize is just how fast chemical enrichment has occurred. So over here, once again, I'm just showing everything with linear scale because it's easier to grasp and to perceive on a human scale. So with the blue line is the result by GalCEM.
Okay.
And then all of these dots come from Silva Aguirre, 2018. Those are metallicity data. And I just placed a linear fit to show a comparison. Once again, with K of 1.4, the slope becomes parallel.
Okay.
Okay. And so this is also an indication that with a K of 1, you get most of the chemical enrichment within the first 3 gigayears, maybe.
Yeah.
And then you're basically already saturating to your average metallicity, which also happens to be the solar metallicity. So the why there's that vertical orange line which represents the solar age. That's where the sun is born. And it just perfectly works out that the metallicity just reaches the solar values.
How fortunate.
Yeah, it's
very good.
Yeah. And for iron also, we see that instead, given that, as we said, more than half of the iron is produced by type 1a supernova, we see that iron takes a little bit slower,
right,
a little bit longer to get produced compared to the total metallicity. Yeah.
About 4, turnover about there. Yeah. Okay, all good.
And all of these follow the brackish notation, so everything is normalized to solar values. So 0 means solar value.
Right.
Yeah.
Good.
So.
Okay.
So these elements are in check. So maybe what we might have next, probably there's a table before the final plot, or maybe there's. Oh yeah,
you got
the big plot.
Oh, there's a bigger
one. So this is Yeah, but I think that this is more interesting.
This is interesting.
So this is the really big plot of this paper, and we defer the discussion of individual elements to future papers. You know, those will be investigated individually, each one of these elements.
Oh, okay.
But
Each of the numbers here is labeling the plot 3, 4, 5. It's not like this is 5 boron and you know.
That's the atomic number.
Got it. Okay.
Yeah.
Yep.
So
Okay.
carbon 6, oxygen 8. Yeah. Yeah, it's a little bit unconventional, but I just wanted to
it's fine.
for people to have that reference.
I just blew it. It's okay. It's fine.
Yeah.
I got it.
No. So you see that the agreement is not perfect because once again we have no dynamics and nothing else, but it's already an excellent agreement. And actually, compared to my point of reference, which was a Romano 2010, there is an excellent consistency of trends. So basically, we reproduce exactly the same trends. So many elements go well. Sodium, magnesium, aluminum, etc. Also carbon and oxygen are reproduced quite well. Vanadium and scandium, so 21 and 23, those are known to not be well reproduced within our model, within our ecosystem, but that's okay. Once again, we will treat it in the future. One thing that might be a little jarring is what happens with nitrogen. And so you see that nitrogen gets an enrichment very, very late. So this is a secondary element behavior. And instead you see that there's lots of nitrogen enrichment that occurs at very low metallicities because nitrogen does have a primary component and a secondary component. So the accepted explanation is that once you introduce the yields from rapidly rotating massive stars, then nitrogen does behave as a primary element. And if I were to include the Limongian-Kefi with rotation, nitrogen is reproduced quite well. But over here, I just wanted to use the yields with a 0 rotational velocity, and that's why we have this behavior.
Very cool. I like this a lot.
So I was very, very happy. So it took a very long time to get to this point, and I might have shed a tear or two after producing this plot. But it's okay.
Popped a bottle of champagne or something. I don't know.
Yeah.
Very cool. Good. So, that's 12.
Yeah, we can move.
Then we have the postage stamp. So I will do the full postage stamp so everybody gets an appreciation for how many plots are on this figure. 1, 2, 3, 4, 5, 6.
It's 120.
110. Yep. 110 figures in a plot. Awesome.
So yeah, this is just the returned masses and the decomposition for each one of the processes included. Big Bang nucleosynthesis, core collapse supernova, AGBs, and type 1a supernova, each color coded.
Let's take a look at.
So yeah, and also this. We really don't need to get into extreme detail with this, but one of the things that is investigated quite thoroughly here in Nanjing University is the isotopic ratios. So carbon 12 to carbon 13, and oxygen 16, 17, 18. Yes. So all of these are observable quantities. And especially we can look at carbon 12 and carbon 13. They are produced at different rates by both core collapse and low to intermediate mass stars. And tracking the isotopic ratios between these two can inform us about what is the past history that brought to this specific type of enrichment. How many low mass stars you had, how many high mass stars you had. Can that give us indications that the initial mass function has varied? So all of these are questions that we're hoping to tackle with GalCEM, but in due time in future papers.
Very cool. Very cool.
And there should be, yeah, this last table. Yeah, there's this other little tool that that we provide with GalCEM. Basically, we're expanding this observational library, and so people can select their element of interest and get an output of all of the papers who contain that given element, so that it can be included in their plots.
Very nice. Very nice. That'll be a handy tool. All right.
And then we have these listings, and I just want to take a look at the data metrics for the interpolants. Here we show the oxygen 16 for listing 1 for the Cristallo yields, so for the AGBs, and listing 2 for the core collapse supernova. And you see that the error in various forms that we can compute at absolute or relative is exceedingly small. So basically there's the yield interpolation tool is really efficient at doing the interpolations correctly. So it's reliable, and anytime that each isotope is computed, the user can see this trained data metrics to check if that given isotope is reliable or not.
Right, sanity check.
Yeah.
Very cool. Exactly. Very cool.
So,
that is GalCEM 1.00. Very nice.
And this was a bit technical. I wasn't expecting to talk for this long, but
JPJ, it's all good. All righty. Eda, I want to thank you so much for walking us through your very lovely APJ supplement article. Thank you.
I had so much fun. Thank you for listening.
And you touched on it a little bit as we went through it. So let me just push a little bit on it. And that is, where do you think we go with this, or where do you take this project in the future, let's say on 2 to 5 year timescales? This is clearly paper 1, and I think you in tone, there was paper 2, paper 3, paper 5, I don't know. And so just, if you want to, where do we go with that? Are there additional observations that can be done that would help with, in particular, maybe certain isotopes are lacking observational data for one reason or another? Is there additional stellar models that could be run to help fill out different scenarios or different completeness in their isotopes from the stellar models? So just sort of where do we go over the next 2 to 5 years?
So the answer is yes to all of what you said. So
okay.
There's not a single no in all of this, but in the very immediate future, our priority is twofold. It's threefold, actually. So the 3 papers that we're working on simultaneously right now is to produce the detailed return rates for the R process elements. So we want to, here we just presented the elements up until zinc. We need the full periodic table.
Right.
And that is a very big problem. And if every time that we look at archive, there's contradictory hypotheses all across the board, but I guess that's a topic for another time. So there are several. For a long time, it was believed that neutron star mergers could have explained the abundances of our process elements, but recent studies have shown that they're absolutely insufficient. They come too little, too late. But at the same time, what are the alternative hypotheses? There's no confirmed observational hypotheses for example, collapsers. Collapsers now are a big candidate. But in order to have collapsers, you have to have a certain rotational velocity for the progenitor. Right. And can you get enough collapsers at a sustained rate also later on in the chemical enrichment history? And that's very much debated. Okay. I'm already spoiling. I hope.
No, they're advertisements. They're free advertisements on where you're going.
Yeah.
It's all good.
So no, and basically it is very problematic. And we do offer some candidate solutions, but we also highlight what possible problems could still exist and might not be solved in just the next couple of years. It might take a little longer, and more detailed observations, more detailed cellular yields, and so on. Yeah.
Very cool.
And then obviously it's also very important to have a radial dependence for basically we need to transform this code from a one-zone model to a multi-zone model. Because there is a clear gradient, especially in the Milky Way, of abundances of chemical elements.
Right.
And so that's the one of the very next steps. And lastly, we're also working on introducing a variable IMF. So these are the three urgent projects, and then we also have. Let's keep the other ideas for the future.
Okay.
Let's save
a boatload right there. That's a boatload.
Let's save. Yeah. Let's save our future ideas for the future, because it's super already cool. A lot.
Very cool.
Yeah, but several people are already working on this, so hopefully we will pick up the pace.
Nice. Well, I really look forward to seeing this topic and field advance over the next couple of years with tools like GalCEM. I think it'll be very nice. Cool.
Thank you so much.
That will do, everyone, and I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.